Hello developers. Ever built an API endpoint that makes the user wait and wait because it's busy sending an email, processing a file, or generating a report? That's a huge drag on user experience and can cripple your app's performance. But what if you could notify the user instantly that the request is being processed and handle all that heavy lifting in the background? Well, that's exactly where BullMQ comes in. So when do you actually need BullMQ? Well, whenever you have a slow task. Don't make a user wait for things that can happen later. When you have a resource intensive task, you can offload the heavy processing to the background workers and keep your main application fast and responsive. Or let's say you have a scheduled task. You can run those tasks at a specific time or on a recurring basis in your BullMQ worker. So some common real world scenarios would include sending emails and notifications, processing media files, resizing uploaded images, transcoding videos, generating reports, running a chunking pipeline on an uploaded PDF, or let's say your user wants to schedule cron jobs. Let's say the user wants you to generate a report for him every Monday. All these kinds of tasks are perfect candidates where BullMQ worker can really help us out. All right, so let's break this down visually. On the left, we have our backend or our job producer. In our tutorial, this is going to be our NestJS application. When a request comes in, like a user uploading a video for processing, our application does not handle the slow task right then and there. Instead, it creates a job. A job is essentially a small packet of information describing the work to be done and the required information about it. So our job producer enqueues that job, pushing it into the central queue, which is in Redis. This is not just an array in memory. BullMQ uses Redis as its backbone. Redis is super fast and persistent data store. That's why it's very reliable. It holds all of the jobs, making sure that no tasks are ever lost, even if your application crashes or restarts. Finally, on the right, we have the real workhorses, the background workers. These workers can be part of the main application process itself, or they can be completely independent of our main application. Their only purpose is to watch the queue for new jobs and process them accordingly. When a job appears, a worker will dequeue it, pulling it off the list and start processing it. This is where the actual email gets sent, the video gets transcoded, or the reports get generated. And notice how there are two workers in this diagram? Well, that's the key to scalability. You can spin up as many workers as you need across multiple servers, all pulling jobs from the same queue to process jobs in parallel. This allows you to handle a massive amount of work without slowing down your main application at all. This architecture helps your application feel instantaneous to the user while ensuring all the hard, slow work still gets done reliably in the background. It's a fundamental pattern for building modern and scalable applications. Now let's jump into the code and implement this from scratch. Cool. Let's start off by scaffolding our NestJS application with the Nest CLI. Now we'll install BullMQ. Now we'll register BullMQ in our root app module. We need to provide it with a connection to Redis. Now let's create a module where we'll have our background jobs, workers, and queues. Now let's register a queue. Now let's create a worker. A BullMQ worker in NestJS is nothing but a provider that has the decorator of processor on top of it. We need to provide the name of the queue that this worker will listen to. And our class needs to extend the worker hosts class. Worker host by NestJS BullMQ. Now we see a little problem. It says non-abstract class does not implement inherited abstract member process. What this means is we need to create a method here by the name process. And that's it. Now we're ready. Anything we define in this method is the actual job processing logic. Let's have some dummy logic here to simulate a job being worked. Perfect. Now we have a queue and we have a dedicated worker. Now we need to build a way to add jobs into the queue. For that, we'll build a simple API endpoint that the user can post their job data to, and that will just add the job into the queue. Okay. We need to inject our queue into this controller. Inject queue. We need to provide the name of the queue. Simple. Now we provide a name of the job and we pass in the data that we receive from the API input. And that's it. Now we have a queue, we have a worker, and we have a way to add jobs to the queue. Let's see it in action. Let's start our application. I've created a post request to our endpoint, and we're sending in data as JSON. Send it. We get an immediate response. This is what we get from BullMQ when we insert a job. The API response can be customized to notify the user that their job is being processed. And our job has been completed. So essentially, the user sent us the data, we inserted it into the queue, and then the worker picked it up and processed it. Now let's see what happens if we insert 10 jobs or 5 jobs. Cool. All these 5 jobs were inserted, and they are being handled by the worker sequentially. So each job takes 2 seconds to complete, and they are being completed serially. But what if we want our worker to process multiple jobs at the same time? Well, this is where the concept of concurrency comes in. And this is especially important for jobs which are heavily IO based or heavily rely on asynchronous tasks. As you can see, our job logic is highly asynchronous, making it the perfect candidate for concurrency. So how do we add concurrency to our worker? Well, in the decorator, we just define it. Let's say we want the concurrency to be 5. This means that our worker will process 5 jobs at once. So before it was processing all these jobs serially, one after the other. Now once I insert these 5 jobs, all of them will be handled at the same time. Let's see it in action. Waited for 2 minutes for this to resolve, and all of these jobs completed at the same time? What if the concurrency is 2? Now our worker will finish all these jobs in 6 seconds. It's going to take up the first 2 jobs, handle them in 2 seconds, then the next 2 jobs in 2 seconds, and then it'll handle the last one remaining job in 2 seconds. Okay, let's see. Another 2, and then the last one. Perfect. Now let's see how we can handle jobs which have a potential to fail. So what we'll do is we'll manually throw an error to showcase a job that fails. Now we will configure BullMQ to handle jobs that fail. So how we can do that is, when we're adding a job, we can specify what kind of retry strategies do we want it to have. So let's say we want our BullMQ worker to give 3 attempts to the job. We simply pass in the options, 3 attempts. We can also define a retry strategy. We want our worker to back off for, let's say, a fixed duration of 2 seconds in between each of the retries. So we want it to be fixed back off with a delay of 1 second. And yeah. So now, when we start this job, it's going to fail. Our worker is going to try again, and then it's going to fail, and then it's going to try again. Let me add some more logging. Cool. Let's see it in action. First attempt, then it waited for 2 seconds and tried again for the second attempt, and then for the third attempt, but the job failed. Now let's see how we can handle repeating jobs. So let's say in the job data, the user will provide us with a cron pattern, and we want these jobs to execute based on the cron pattern that we received from the user. So we can create a retry strategy, a repeating strategy. We say repeat, and here we define the pattern. And that's it. Now we just want our user to send us the cron pattern. Let's say we want, the user wants this job to run every 10 seconds. Cool. The job has been created. Now every 10 seconds, this job will execute. Let's wait for 10 seconds. Now BullMQ will manage it on its own. We just provide it with a repeat strategy, and that's it. That's how you handle repeating jobs. Now let's discuss how we can track queue events and worker events. Worker events are specific to individual worker, while queue events are global events pertaining to that particular queue. And these events can really help us understand what's going on inside our queue and our workers. Let's start off with building a worker event listener. It's very simple. We just use this decorator, and then we have a list of events that a worker emits. So let's say whenever we have a job that's being completed, we want to let's just say whenever a job is completed, we just want to log out its job ID. It can contain any logic that you want, but for simplistic purposes, we're just going to be logging it out. Cool. Now let's see our worker event listener in action. Now we've added a repeating job that repeats every 10 seconds. Our worker event listener is working as expected. Now let's also build out a queue event listener. Well, it's going to be a provider in terms of NestJS, and it's going to have a decorator called queue event listener. Queue events listener. It's going to extend the queue events host. Queue events host by BullMQ. Yes, sir. You have to give in the name of the queue. And now simply we use the decorator on queue event. Again, this also provides a list of events that we can subscribe to. Let's say we want to see whenever a job fails in this queue. Queue events receive the job ID. They do not receive the complete job object. Let's make our worker throw in our job logic, throw an error to simulate a job failing. Let's see it in action. Cool. Now that we have created a queue events listener, we need to register this as a provider in our module. Nice. So now it's registered. Let's just simplify our job a bit and remove all these retry and failing strategies. Let's keep it simple. Start the application again. Cool. Now let's trigger it. Oh, object. Oh, okay. I understand what's wrong. Let's now it'll work. We just needed to destructure it. I'll hit it again. And it should fail now. Job with ID 2 has failed. So now we understand how worker events listener and queue events listener function. Now let's talk about scalability of these workers. You must have observed by now that our worker currently is very tightly coupled with our main application. That means that only one instance of a worker is available per deployment of the main application. What if we want to have 10 workers being available for our single application deployment? Well, we can do that by decoupling the worker from our main application and deploying them separately. We shall do that now. I will create a standalone NestJS application and that can be deployed on its own. So let's start. We'll create the standalone application in the same monorepo, ensuring it's easy to manage. Perfect. Let's create a sub app and turn this into a monorepo. Great. So now we have two applications. One is our main application by the name BullMQ stuff. Poor naming choice, but this is what we have. And we have a separate application by the name worker. Let's make this as a standalone application. So instead of it listening to ports, we don't want it to listen to any port, because the only way it's going to receive information is through Redis. So we'll turn this full application into a standalone application. Create application context. Great. Now it will work as a standalone application. Now we just repeat the process. We register the bull module. Let's keep it simple and register the queue here itself. Great. Now let's just copy over the worker. Let's clear the worker from the main application. So now our queue event listener is in the main application, because we want our main application to consume all these global queue level events, and the worker event listener resides with the worker. Now let's deploy. Now let's start both these applications. This command will start the main application, whose name is BullMQ stuff. Let me just split the terminal and start the other app as well. Cool. So now our main application is running in the terminal above, and the bottom application 6379 should be 6379. Yeah. Okay. We don't even need a controller, because we don't have, this is not an application, this is a standalone application. This does not listen to any port, so we don't even need a controller. Let's just delete this. Great. Should be up and running. Yep, it is up and running. So now I'm going to add a job through the main application through the API, and my worker application is going to consume it. Just hit it. And our worker has executed the job, and our main application is still there. Okay, so I think in the job logic, yes. So we were failing the job, right? So our worker, now it's just saying the wrong thing here. Should be saying failed, but let's do it again. So our main application has the queue events listener that subscribes to jobs when they fail. And our worker application, we are manually failing the job. Cool, so we added a job. It was executed by the worker, but it failed because we threw an error. And then the main application had the queue event listener, and it notified us that job 4 has failed. Now let's not fail our jobs. And let's deploy multiple instances of our worker application. Cool. So now we have one main application and we have 2 workers running. Let's change the concurrency to 1. That means one worker will only execute one job. Let's restart the main application as well. And what we want to do is let's insert 4 jobs at the same time. Now we'll insert 10 jobs at the same time, and we have 2 workers, and they're going to run in parallel, and they're going to pick up jobs individually and execute them. Just hit this endpoint. Done. Now, see, they're executing these jobs in parallel. And all of them have different IDs, which means they're subscribing to different jobs. And they're dequeuing jobs at the same time. I think now we understand how we can introduce parallelism and help our application scale by decoupling our worker from the main application and deploying multiple instances of the worker to execute jobs in parallel.